This video is about induced EMF in a coil that is turning in a magnetic field. We'll discuss two different cases. First, when the coil is rotating clockwise or anti-clockwise in the plane of the paper or screen, and second, when the coil is flipped. You can picture the first case like this. The direction of the magnetic field is into the page or screen. It doesn't matter whether we rotate the coil clockwise or anti-clockwise. As long as it remains in the plane of the paper or screen, the number of field lines that cross the coil is unchanged. As a result, magnetic flux through the coil is also unchanged. The formula that expresses Faraday's law tells us that induced EMF is a result of changing magnetic flux. Since there is no change in magnetic flux, no EMF is induced in the coil. The second case is when the coil is flipped. If it is not fully clear what flipping means here, picture the coil being rotated by 180 degrees about this axis. After the coil is flipped, it ends up in the position that you see on the right-hand side. Let's consider the situation from the coil's perspective. What practically happens is that the direction of the magnetic field through the coil is reversed. So if we take the magnetic flux through the coil to be phi before it is flipped, then the flux through the coil after it is flipped is negative phi. The change in flux through the coil is final flux minus initial flux, so negative phi minus phi, which gives us negative 2 phi. Let's apply Faraday's law. Since the change in flux is negative 2 phi, we get that the induced EMF is equal to negative n times negative 2 phi divided by delta t. Simplifying, we get 2 times n times phi divided by delta t for the induced EMF in the coil. Therefore, when we flip the coil in the field, there is an induced EMF in the coil. This wraps up our discussion of induced EMF in a coil that is turning in a magnetic field and concludes the final video of subtopic 11.1. In the first video of subtopic 11.2, we'll start learning about alternating current generators.